Episode 98, New Nova. Welcome back to another edition of the Syzygy podcast. My name is Chris Stewart. I'm sitting in the office of Dr. Emily Brunsden here at the University of York. And Emily, you are still here.
I'm still here. I'm still the combined mass of two people.
You are still, as we say, on the outside of your child. Any day now, any minute now. Who knows? We may not even finish this podcast, but we'll see. We'll see what happens. Welcome back. I'm really glad to see you again, back here for episode 98. At this rate, we might make it to episode 100 before the baby comes along. You never know.
We'll just have to see.
Emily's sitting there looking at me going, no, I really hope it's not another 2 weeks. We shall see how we go. Listen, today we're going to be talking about a topic which just wandered across my screen a little while ago, which is about something that I didn't even know existed at the time. Is this a new thing to you, Emily?
It's a new thing in all the senses of the word new, isn't it?
It's a brand new thing. We're talking today about a brand new phenomenon been described called not a supernova, not a nova, not a sort of plain vanilla variety, common or garden variety nova. This is a micronova. So we're going to unpack that a little bit today and go, hang on, I think we know what a supernova and a nova, we're talking explodey things.
Yeah.
Stars go boom kind of thing.
New thing.
But this is a micronova, which almost sounds kind of cute. It almost sounds like, who wouldn't want one of those?
Baby nova, if you will.
We'll be talking about that today. And the really exciting part of this is that we're back to actually controlling the destiny of modern astronomical research here on the podcast, because we're actually going to be able to link it back to something we've talked about in recent times. But I'm sure that'll come up in the course of the episode.
I know the real reason why you chose this topic, Chris.
It's not true. It's not true. I didn't choose it just for that. Listener, you'll know it when we get there. Okay, so Emily, where do we start with this? How do we unpack this? What's a micronova?
Well, if we go just unpack the word, it's pretty straightforward and
sure.
that it does what it says on the tin. So,
which is
helpful.
Not always true in astronomy, as we've found. Things don't always get named around what they actually are.
There's almost two categories, I think, in astronomy. There's kind of the very obvious, which is like that looks like a hole that's quite dark. We'll call it a black hole. Or there's kind of the historical, which is, something like, well, we'll call it this because we used to always call it this, and we called it this 500 years ago, even though it makes absolutely no sense to call it that anymore.
Yeah, even though we've learnt much more now, or we know that it's this complete different other thing, we'll just keep calling it that. Yeah. Okay. But no, this one, because it's brand new, it is what it says on the tin.
It is, yeah. So micro, meaning
small.
Yeah, well, even very specifically micro, meaning 10 to the minus 6.
Okay,
or a millionth.
So it's not just that use of micro meaning like this is much smaller than the other one. This is actually specifically, no, we're talking size here.
Yeah.
Okay.
And nova. So a nova being a stellar explosion.
Right. So this is a very small stellar explosion.
Yeah.
That sounds almost too straightforward for something which we've literally only just found. So it sounds really simple. Why haven't we seen these before?
Well, these are the small versions of things that we have seen before and do understand reasonably well. So maybe we should go sort of wind the wheels back and go and look at what actually novae are.
I think that's a really good idea, because I think this came up only, within the last couple of episodes, where at some point supernovae came up. And then I suddenly went, hang on, aren't novae a thing? And I suddenly realized I don't even know what a nova is. So maybe we should do a little wander through the landscape of how stars go boom in different ways.
Yeah. Well, going boom is kind of a bit dramatic.
Is it? Okay. I'm overstating that?
Well, potentially. But let's say, so nova, if you just, it comes from the Latin, it's pretty obvious meaning new, right?
Right. Yeah.
So I think even the phrase nova, or novae as in the plural, comes from the description of new star, nova stella. So
right. Turns up in our English word novel. And other similar words. It's new.
Yeah, new. So it was first used to describe things that appeared in the sky that weren't there before.
Right. Okay, so suddenly you've got this new bright thing in the heavens as you're looking up.
Yeah.
Right. This is in antiquity. This is not necessarily when you're looking with telescopes or anything like that. You're just looking up and go, hang on, that wasn't there yesterday.
Yeah.
Big bright thing. New star.
New star.
Right. Nova.
Yeah. So there are lots of different types of nova, and we'll come to the kind of the supers and the hypers and whatever in a little bit.
Sure.
But if we just go with the ordinary nova, that what we call nova today, there are kind of a sub sort of classification of a larger group of variable star objects that we call cataclysmic variable stars.
Sounds good.
Yeah.
Again,
sounds quite dramatic.
What it does on the tin, it's a star, it's varying, and it's pretty nasty.
Yeah.
Yeah.
So, well, it just sort of means that there's kind of no way out in some senses for these stars.
Well, this is not going to settle down into
Yeah.
something happier. This is the end of the road.
Yeah, pretty
Right,
much.
right.
So they all are variations of the same kind of system. And the system is you've got two objects in a binary system, so two stars. One of those stars is a white dwarf, which is a very, very compact end remnant of a lower mass star.
Okay.
Yeah, so we've spoken about white dwarfs when we talked about stellar evolution, when we talked about what the sun's going to become in its future.
Right, so this is our future here.
Yeah,
Right.
yeah. So these little white dwarfs, so that, well, I say little. They are little in terms of size. They're big in terms of mass. So the general analogy is you've got the mass of the sun compressed into something the size of the Earth.
Right. Okay, that gives us something to hang on to there.
Yeah. So, very, very dense little end remnants of stars. Now, they are in a binary system, and it's not just any binary system. It's got to be a very, very close binary system with another star. And that other star hasn't gone through its full evolution process yet.
Okay, right. Does it matter what size that star is?
So it's typically a red giant. But it will have to have been. It's kind of this weird sort of backwardsness where because the bigger you are as a star, the faster you evolve.
Yeah, how does that work?
Yeah, because you've got more mass, so you go through your fusion processes quicker.
Yeah.
So the star that was there before it became white dwarf was actually the bigger star of the two in the binary.
Okay, right. And so it's gone to a white dwarf already.
Yep.
It's already got there. And now there's other ones hanging around going, wait for me, hang on, not done yet.
And so the second one's now got to the point where it's starting to go through that phase of evolution. And one of the big ones is going to a red giant, which means it puffs up, becomes really big. And it becomes actually so big and the orbit is so close that actually the material on the very outside layer of the red giant star is actually more gravitationally attracted to the white dwarf than it is to the star.
So it starts ripping off the outer layer, starts pulling it apart.
Yeah. So we
Wow.
get mass transfer.
Right.
So this mass is moving from the red giant to the white dwarf, and it's accreting in what it's called overfilling its Roche lobe, which is quite
That doesn't sound healthy. Filling your Roche lobe. What does that mean?
So your Roche lobe is kind of your area of gravitational influence. That means that's your atmosphere as a star. And if you overfill it, then it means that you're going to push it onto the other white dwarf.
Right. Okay. So the not white dwarf star, the other one,
Yep.
is overfilling its Roche lobe, not
Yep.
the white. Right. Okay. Yep.
It's overfilling, so that means the mass is being transferred. And so it kind of goes in a little tail stream and then ends up in a accretion disk around the white dwarf. And that's kind of the basic sort of setup that you need for all these types of novae.
Right. And I'm guessing that from what you described there, that's a fairly calm and low energy occurrence.
Yeah.
Is it?
Well, not so much.
No?
Because if you sort of cast your mind back when we did talk about white dwarfs are actually pretty, intense objects.
Yes, I do remember you saying.
Yeah, quite dense, right? But they're also very hot and they also spin incredibly fast. So there's a lot of energy going on in these systems. And so when we talk about novae, you can break it down perhaps into there's three main types. There are more, and there's lots of ways you can kind of subdivide all the other types as well.
Sure. Because the universe isn't that simple.
No.
Okay, let's talk about the main ones.
But we got three main types. So if you start with your classical novae, now these ones are they're called classical because they're the first ones and the sort of best studied ones. We know about 400 or so of these classical novae systems. So this is where the white dwarf's accreting. That accreted material goes into the atmosphere of the white dwarf. Mm-hmm. So it's kind of making it a bigger star, in effect, with this extra atmosphere. But the white dwarf's really hot, right? Because it's the core of this old star.
Yeah.
It used to be millions of degrees.
And it's really dense, and it's spinning really quickly. Probably got ridiculous magnetic fields as well.
Well, yes, we're going to come back to those.
Yeah.
Yeah. So the material accretes onto it. It gets onto the atmosphere. It gets heated, and it actually gets heated so much that the new material that's going onto this white dwarf actually ignites.
As in, it turns on its nuclear reactions.
Yeah.
On the outside.
On the outside.
Holy cow.
Yeah.
That's not what you normally hear about. It's normally right down in the core. And this is, wow.
Yeah, so the surface of the white dwarf basically ignites in what we call a thermonuclear explosion.
Wow.
20 million Kelvin or something like that.
Wow.
Yeah.
Okay.
So, it's quite a significant event.
Yeah.
And you get this bit of fusion going on, therefore. So, and it's actually interesting. It's the CNO fusion. So again, if you go back to some of our earlier episodes, we talked about actually very large stars. They tend to do this carbon, nitrogen, oxygen fusion process in their cores rather than the straightforward hydrogen to helium fusion. So that's kind of the same pathway of fusion.
Yeah, I can't remember which episode we talked about that in, but we definitely have. So we'll dig it up and throw it in the show notes.
Yeah. So then that fusion, sort of that ignition, basically creates a bit of an explosion, expels the atmosphere off the surface of the star. And what we see is that the star it gets super bright. It goes, several hundred times potentially brighter than it used to be.
And that's the nova.
Yeah.
That's the bit that we would have seen in antiquity before we knew anything about these things. Or still now. There's something new and bright up there. And it's that sort of thermonuclear explosion going off.
Yeah. And then the atmosphere is expelled, it sort of slowly sort of fades away. And these stars, there's quite a variation depending, I guess, on exactly what mechanics you've got going on in your system. You can have ones that kind of rise quite quickly within a few kind of days. You can have ones that take sort of tens of days. And then they can tail off and they take anywhere kind of a few tens of days to maybe 80 days or something to fade away again.
And is that a singular event? Like, does that sort of blow away the other star or stop? Or can it sort of come back and continue and do that again? Like, what happens after that?
That's a good question. So these classical novae are ones that we see that are generally one-offs.
Right.
Or at least they're one-offs as far as we've seen so far. The second type, if you like, of novae are recurrent novae.
Okay.
Which do exactly what you just say. They just do it sort of, I wouldn't say regularly because it's not sort of super well periodic, every 5 years a star is going to do this.
Right, yeah. It's not regular, but it's periodic.
Yeah.
It'll happen again.
Yeah. Sort of semi-regular.
Right.
They're sort of roughly every whatever number of years.
Right. And that's because the other star is still there. And it's going, that was a bit rough. But the gravitational system is still there. And so the other star will continue to lose its mass over to the white dwarf.
Yeah.
And it'll just build up again.
Yeah.
And we're going to go through this one more time.
Yeah.
Okay.
Exactly. So there are current novae. We know of about 10 of them.
Okay.
They're quite exciting, actually, to look at. They're very different to the types of variable stars that I'm used to looking at. I used to sort of see these light curves or the changes in brightness, which just all over the place. They're I can't decide if they're very disturbing or very exciting.
Why not both?
Yeah,
Why not both?
So one of the most famous ones, for example, is one called R.S. Ophiuchi. That's gone off 7 times between 1898 and 2021.
Right. Okay. That's quite a lot.
Yeah.
Yeah.
So we're talking about sort of tens of years
Yeah.
that these things tend to go off. And maybe there's even some thought that actually all novae are recurrent. And it's just that we haven't observed the other 400 for long enough yet.
Yeah, either the timescale's too long or we missed it in some way. Or
Yeah, probably the timescales are too
Yeah.
long, so maybe they're more like 1,000 years to 100,000
Right.
years between each event because
Right.
they're accreting slower.
And let's face it, 1,000 years is not a lot. That's a blip. That's a tick of a watch on the cosmic timescale. It's a long time for us, but the universe would just shrug its shoulders at that.
Yeah.
Yeah.
So you've got classical novae, recurrent novae, and then there's this sort of a third classification, which is one of the main ones, is dwarf novae.
Mm-hmm.
These are pretty similar to the recurrent novae, except they're quite a lot fainter. So they're just kind of smaller versions.
Right. Okay.
Of those. So you don't get quite the highest temperature, not quite as big a brightness, and they tend to just be, smaller, recurrent little
Yeah,
novae.
but the same mechanism.
Yeah.
Same idea, just smaller.
Same stuff, but yeah.
Okay.
Yeah, so those are our novae. And with the we sort of think that they're pretty common in this. Well, it's hard to say what's common and what's common and what's not common. Let's try and put some perspective in it. I mean,
Sure.
These very tight binary systems themselves are not common,
Right.
Because you've got to get two stars in a binary quite close together, and then you've got to evolve one, and we've got to catch them in this middle sort of period of their lives where one's evolved and one's not.
But binary systems are common, right?
Binaries are common, yeah.
But not the specific type of binary, where it's nice and tight in the right sort of period of their evolution.
Yeah.
You've got to get that just right for this to happen.
Yeah, so if you just go out and look at different stars, then we say something like half of them are in binaries, maybe-ish, and then there'll only be a very small fraction of that half of which are actually in these tight systems. But there's lots of stars in the galaxy.
Yeah, and as we've said before, small overall likelihood times a very, very large number gives you enough.
Yeah.
You can observe those, no problem.
Yeah. So we think that maybe in our galaxy we see there might be like 50 of these novae go off every year.
Right.
And we tend to catch maybe about 10 of them.
That's not bad.
No.
That's good stats.
Well, considering some of them can be on the complete opposite side of the galaxy.
Yeah,
right?
like hidden by a lot of stuff.
Yeah.
Yeah.
It's not too bad.
Yeah, okay.
So I guess 50 a year is kind of broadly, moderately frequent.
That's enough to get a career out of as an astronomer, I think.
Not too bad. Now, I guess the question is, so that's a nova. What happens when you turn up the dial a little bit?
We're getting up into super territory here.
Supernova. Now, here we have to actually sort of sit down and say this is where astronomers have done the second part of the naming thing that we talked about before, where there's a bit of historical namingness that's going on here that's not necessarily particularly useful when it comes to understanding these objects.
Okay. How so?
Well, so there's two very different types of supernova that occur, and they occur from completely different types of systems. So there's basically what we've just been talking about, these classical novae, etc., where this gets to a point where you dump too much mass onto your white dwarf. And a white dwarf is holding itself up by a piece of physics called electron degeneracy pressure.
Okay, now we've talked about this one before, so let me see if I can dredge this one up. When you're collapsing under your gravitational weight, right, the force of gravity is pulling everything down towards the center, towards its gravitational center, yeah? And that'll keep going until something stops it. Yeah. And the sorts of things that'll stop are things like in a normal star, right? The nuclear reactions that turn on when things get really hot and high pressure. The nuclear reactions will, creating energy and particles and so on, flinging themselves out. And that pushes out, that's a pressure pushing outwards. And so that ultimately you come to a balance. If you push past, that is the next step, electron degeneracy?
Step down, yeah.
Okay. And so that's when the quantum idea of electrons are a type of particle called fermions that can't be in the same state. And what that means to all intents and purposes here is you can't get them really, really close together without causing problems. And so you reach this limit where everything's squished down so much that all the electrons are going, we can't go any further within the laws of physics. Thanks. We're not allowed to. And that creates its own kind of energy pressure pushing outwards, saying, no, we can't get any smaller. And that's what causes that balance. And that's where you are with a white dwarf.
That's where you are, yeah. Because so there's no nuclear reactions going on inside the white dwarf. That's all done and dusted. Instead, you've just got this electron degeneracy pressure holding them up.
Right, okay. And so you've reached that bound, but then you start adding more mass.
Yeah, so that this pressure can only last for so long.
Because the laws of physics, there's ways around them. Yeah? Like to a certain degree, all you've got to do is offer the laws of physics an escape route and it'll take it. And if you build up the energy to such a degree, the mass to such a degree that you go, tell you what, all right, it's really hard, but here's a way you can get around this. We're just going to turn on this really difficult kind of nuclear or particle physics reaction to turn this into that. And then you're allowed to do it. And in this case, it's what? It would be electrons. What would they do?
Well, if you put too much mass on this electron degenerate ball, and we know exactly actually how much mass that is. It's at 1.44 solar masses. Okay. Also known as the Chandrasekhar limit.
Right, that's what that is. Yeah.
From Chandrasekhar, the astronomer.
And that's like 1.44. That's not sort of one and a bit, 1.5. That's pretty accurate. Like, we know this well.
Yeah. So that's 1.44 suns. You can't be bigger than that. If you do that, then what happens? Yeah, your electrons are so they can't hold it up anymore. So basically, you just squash them all together with the protons that are in the nuclei of the atoms that are in the star. And then you squash them together. One electron plus one proton effectively gets you a neutron.
Yeah, which, like, that can happen around us in the world, does happen around us in the world, but en masse in a squished together star, it takes a lot of energy to turn that on as a big reaction. And so that's why you only get it happening in these extreme environments. And so what happens then? You're turning a white dwarf into what, a neutron star?
Neutron star.
That's the next step down.
Yeah.
Okay.
So, but that whole process, so your white dwarf accreting all this stuff and then getting to the point of getting to that collapse. Now, that collapse happens incredibly quickly because another thing that degeneracy means is that basically the whole thing is one interconnected, locked system. So if one little electron and one little part of that white dwarf basically switches over into a neutron.
I think I'm just going to do this thing. Oh, we're all going to do that too. And then suddenly, wow.
The whole thing just goes boom, basically. And you get a huge collapse, very rapid collapse, which actually means the outer layers of the white dwarf start to collapse. Well, I always have this image in my head of them hanging in the air, a little bit like Roadrunner, off the edge of a
Wile E.
cliff.
Coyote off the edge of a cliff, not knowing it's supposed to collapse yet.
Yeah, and so you get very rapid collapse, and then you get the rapid collapse of the atmosphere after that. Now, that's huge amounts of kinetic energy because you've got basically most of the mass of the white dwarf collapsing down incredibly quickly, and then it bounces off whatever's core is there.
Well, yeah, because the bit inside will have already turned into basically neutron star, which is like some of the densest stuff that you can find. That's about as dense as you can get, and it's rock hard. So collapsing down and hitting that, you're going to bounce.
You bounce
really hard.
You bounce really hard with huge amounts of energy, and that is your supernova.
Wow.
So it's a very special type of supernova because what's happening here is that you're going from an object which is a white dwarf, which has sat around probably as a white dwarf for some time, and then you're just piling on the mass till it can't go anything further, and then it's transforming into this supernova, which we call a type 1A supernova.
Okay, that's a 1A, all right, which implies that there are other kinds.
There are other kinds.
So that, before we go on to the other kinds, the type 1A, first of all, are they the most common that we see of supernovae?
They're not the most common, but in some ways they are. I'm going to make some enemies here. In some ways they're the most special type.
Right to Emily, it's not my fault. I didn't say that. If you're a type other supernovae expert, that's up to you. That's between you and Emily. But they're interesting.
They're very, very famous because we can use them as really good distance measurement.
Right. These are the ones that we talk about as standard candles.
Exactly.
Because they happen the same every time.
Yeah, everyone has gotten up to 1.44 exactly solar masses.
Because that number is so specific. It's you reach this number and it happens.
Yeah.
And it's going to happen the same, which means when you look at one, you know what that thing is, you know what it's going to do, and so you can use that to figure out, well, how far away is it?
Yeah, you know exactly how bright that supernova was intrinsically when it exploded, and that's the key. If you know exactly how bright something is intrinsically, you can tell how far away it is.
Right, and so that's been used to help us understand distance scales in the universe, and in particular, in recent decades, to work out that the universe isn't just expanding, it's accelerating, which is confusing, and that's dark energy. And we've talked about that before, and we'll talk about it again in another podcast, I'm sure. But that's type 1A supernova.
Yeah.
So, okay, from the naming, I'm guessing that not only is there a type 2 supernova, but there's a type 1B at least as well.
Well, yeah, so you can delve down into the types quite specifically depending on exactly what chemical abundances you're seeing, which tells you a little bit about the white dwarf that exploded, for example. Do you see more carbon? Do you see more oxygen? That kind of thing. Do you see hydrogen lines in spectra? That tells you something about supernova. But broadly, you've got the type 1As, and then you've got the type 2s. Those are the two big categories. Okay.
So the A is we're not going to spend too much time worrying about the A part of type 1As. Type 1A, type 2.
Yeah.
Okay.
So type 2s are actually very different systems in a way. I mean, the physics is kind of the same, but the origin, we don't actually have this binary anymore. So it's nothing to do with binaries, type 2s. They are just very, very big stars. And so we're looking at stars that are at least 8 times the mass of the sun when they are on their main sequence, their main fusion part of their life. And those stars are basically so big that when they start to collapse the core down, what would be a white dwarf just can't support them, basically.
Yeah, just whistles past that. It's like, I'm already over 1.44. Let's just not have this argument. We're going to go. Does it go straight to the neutron stage then?
It does, yeah.
Just bypasses the whole electron degeneracy thing.
Yep.
No, I haven't got time for that. We're too big. Yeah, okay.
So they go straight to neutron star, or if they're really, really big, then if you get past even neutron degeneracy pressure, then you're stuck in the final part of trying to compress mass together.
What have we got left? Well, let's just break all the laws of physics and just black hole, straight to black hole. Doesn't matter anymore. Okay.
Yeah. So that's if you're maybe above 20 solar masses as an original star.
Okay. And what proportion of stars are we getting to at that point? I think I remember you saying that the sun, which is one solar mass, hence the name, is it's fairly ordinary. It's fairly average. So by the time you're getting up to things which will do a type 2 supernova, how many of those stars are there?
They're all really quite rare.
Okay.
So the sun's already on the heavier side of normal, if you like, but it's in kind of the top of the. If you were to make a graph of here's all the masses of all the stars and here's their occurrence, then the sun's kind of just a little bit to the heavier side of the peak of that curve. Sure. But by the time you get to 8 solar masses, they're quite rare. By the time you get to 20 plus, I mean, these are very rare. Okay. At least in the universe, in the Milky Way and the galaxies that we have around us today. Possibly, as we've spoken about in the last few episodes, they were more frequent in the early universe, but we won't revisit that.
Just go back and listen. Look, I think our show notes are ultimately just going to become links to our past episodes. It's going to be much easier that way. Just go and have a listen. It's in there somewhere.
Follow the little web trail. But so they're certainly not as common, and even type 1As, are not super common because you need to set up the special binary system for it to happen, and it needs to reach its end of life. So we expect pretty much all classical novae to potentially end in a type 1A, so long as the second star has enough mass to donate. I guess if it didn't have enough mass to donate, then it would just sort of fizzle out, wouldn't it?
Yeah. You might have sort of a few repeating novae, and then it says, "Oh no, we've got nothing left. I got nothing left to give you. What do you want?" And it just would then just be a white dwarf rotating around a white dwarf?
Yeah, just a binary white dwarf system, Okay. Which might eventually lose energy and merge, but that's another story again.
Yeah. We could do mergers another time. Yeah.
So that's supernovae.
Mm-hmm.
And then,
of the various kinds.
Yeah. So one type which is related to the other novae and one type which is not.
Yeah, and so you were saying a minute ago when we started talking about supernovae, this is where the naming doesn't quite line up that's because these are two very different things.
Yeah,
but we give them the same name.
It's interesting because I think in the perspective of this episode, when we talk about novae, we're really only interested in these binary systems. And even when we come back to our micronovae, we are still talking about these binary systems. So we can draw that line of this is one family of novae, and then that's all the other stuff. But I guess from a physics point of view, the fact that you're pushing through things like electron degeneracy pressure.
Yeah, it's just how you get there. If you're not big enough as a star, you've got to borrow some. Yeah. Whereas if you are big enough, it's like, no, I don't need anyone else. I don't need a binary system. I'm going to do this all by myself. Thanks. And it's the same physics, but I can see how if you're into the interesting side of the system itself, there's a lot of richness in there. You've got all sorts of fun stuff around the accretion disks and what's happening to the other star and all of that sort of thing that you don't get with your big honking, brutally large stars that just do their own thing. So I can see the appeal. Sure.
So I guess it would be worth mentioning probably what you correctly pointed out to me that I hadn't thought about to write down actually, is the biggest types of novae explosions.
Yeah, I mean you've got novae, and then you've got supernovae, and then so it does kind of make you wonder. It's like, is there bigger? Like, what's beyond that? Is it ubernovae? Turns out there's hypernovae, as I looked up just before we started. And a hypernova has other names, which I thought were kind of cool. It's called a collapsar, which kind of gives you a bit of a hint as to what's going on there, I guess.
Yeah, it's kind of like a pulsar, but it's collapsing.
Yeah. There was another name for it as well, wasn't there? It was, also been referred to as a superluminous supernova.
Yeah, and I think that's linking back to some other nomenclature we have when it comes to things like galaxies. We have superluminous galaxies.
Right,
And
okay. So a hypernova just sounds like it's just a really big supernova.
Yeah.
Sounds like it's the same idea.
I think you said it was about 10 times an ordinary garden variety supernova.
Yeah, I think that's what they said. It's about 10 times the luminosity, and you can translate that for us. Does that just mean 10 times brighter?
Yeah.
But I mean, I know brightness is kind of weird in astronomy. Like we have an intuitive sense of, that's brighter than that. But it's not that simple in astronomy, is it?
Well, it sort of is. I mean, brightness we measure, or luminosity we measure in watts, which if you break down what a watt is, it's the number of joules per second that are being released.
It's the amount of energy per second that's coming out in all different directions. And so distance plays a part in those sorts of things.
But you could think about the intrinsic luminosity of these objects. So they're just intrinsically 10 times brighter.
Yeah, 10 times brighter. And I'm just looking at the Wikipedia page here. It says you get a hypernova when a massive star, so greater than 30 solar masses. So this is coming back to what you were talking about. That's big.
Very big.
That's on the scale of big to not big. That's a big star. And it collapses to form a rotating black hole emitting twin energetic jets and surrounded by an accretion disk. So
it's kind of like a type 2 supernova, but more so.
Yeah. They usually appear similar to a type 1c supernova. It sounds like we're going in all sorts of directions here. We'll pull back from that one because we weren't here to talk about hypernova in great detail. Point is, it's a really big supernova.
Yeah.
But no other special physics have come in here.
No.
Okay.
Just got really energetic end product, basically.
All right. So that's working our way up the energy scale.
Yep.
We've gone from nova, supernova, hypernova, and then beyond that, just Big Bang, basically, is in terms of sizes of explosions. But turns out we can go the other way.
Yeah.
Which is nova down to micronova. And micro in the specific sense of like a millionth.
Yeah.
So tell us about a micro. What are we talking about?
So we're back to this same family again of our binary systems with the white dwarf and the other star. But what we're seeing here is that instead of a sort of global ignition of the atmosphere of the white dwarf, which is what we saw in the classical novae, this is something a lot smaller. It's a millionth times, millionth of the energy output by the sounds. And what happens is it happens much more quickly. And they seem to be, well, from the first few measurements that we have, and this is the paper that we're going to delve into a little bit, these seems to happen over much shorter timescales and possibly much more frequently than other nova.
So is this, I guess we'll get into this in a second, but, if it's much smaller but happening much more frequently in these kinds of systems, then have we just not noticed them before because they're small? Possibly,
yes. And also because of timescales of observations, it might mean that, if we come and can actually look at what the paper is looking at, or what the data they looked at.
Why don't we do that?
We can dig into that and sort of hypothesize from there why we haven't seen it.
Let's stop talking in generalities. Who's done what?
Yeah, okay. So this is a paper, the press release came out on the 20th of April. It's from Scaringi et al., who part of the team, or the lead team, came from Durham looking at this. And they were interested in looking at some sort of classical, maybe nova variables or stars that might be novae. And there were three in particular that they were looking at. So the three systems are called TV Columbae, EI Ursa Majoris, and Assassin 19BH.
Oh, I like that last one. That's very John le Carré. What's Assassin what?
Well, okay, so the naming of these systems is actually maybe a bit more dull than you might want, maybe got excited about. So the first two, you'll notice that they've got two letters and then they've got a constellation.
Yep, okay.
So that's just an old naming system that we have where we take a constellation and we start with the brightest star in that constellation. We call that alpha. Then beta, then gamma, going down the brightness of all the stars in that constellation. Turns out you run out of Greek alphabet fairly quickly.
Yeah. I mean, the constellations as we know them from the ground might have a dozen or so stars in them, but if you look at that area really carefully, there's a lot of stars.
There's
up there.
hundreds. Yeah. So you run out of the Greek alphabet, and so then you just go into a double Latin alphabet. So A B, A C, etc.
Right. And so what was the first one of those? It was
TV Columbae.
So by the time you're up to TV, like we're talking many stars.
Yeah,
we're
exactly.
a long way down. Okay. And I mean, the thing that I love, just parenthetically, the thing that I love about that is that this is an organizational system of the night sky, which has nothing to do with whether or not these stars are related to each other.
Oh, no.
They are wildly far apart in distance, but they're in the same patch of sky, which makes sense. I think that's kind of funny.
Yeah, so the actual brightness that we see has absolutely no relevance to anything that intrinsically the stars are doing.
Yeah.
A brighter star that we see doesn't necessarily mean it's a brighter star, of course. It just means that it could be a lot closer.
Could just be just up there. Yeah.
Anyway.
So the first two were from that 2 letters and then constellation.
Yep.
Okay, but the last one wasn't. That was assassin something.
Yeah,
Why?
that just comes from a survey, the assassin survey.
Oh, yeah, I think I remember you talking about the assassin. Which, can I just say, I mean, if that was an acronym, like that's pretty.
Well, it's not quite assassin. It's ASASNSN, and I think that's an acronym, but
Right. Okay.
I can't remember what it breaks down into.
Well, let's not lose too much sleep over this.
The 19BH is actually the identifier as part of that survey.
All right. So we have 3 systems.
Yep.
What have they seen?
Yeah, so 3 systems. We know that then, for example, TV Columbae, we've got 2 stars. The orbital period is about 5.5 hours.
So I'm interpreting that as they're really quite close.
Very, very close.
Yeah.
Imagine 2 stars going around each other
Every 5 hours. Yeah. I mean, the moon and the Earth, we're talking a 28-day orbital period. So, wow. Okay.
And the white dwarf is spinning something like with a period of 1900 seconds.
Right. There's a lot going on.
Yeah, kind of 3, 6, 9, maybe 6 minutes, 6 minutes, something like that. Yeah, 7 minutes.
There's a lot happening in these systems. There's a lot of energy here already.
So, a whole star rotating on its axis every, 5, 6, 7 minutes, let's say.
Yeah.
So that one, and then there's the next one, EI Ursa Majoris, is we also knew that to be a magnetic accreting white dwarf, similar kind of stats. So we're talking about a period of 6.4 hours for the 2 stars to go around each other.
So pretty similar.
The white dwarf's going around at 750 seconds or so.
Yeah, again.
Big systems.
Lots happening.
And finally, the assassin one, again, accreting white dwarf. And in this case, we do actually know a little bit more about the companion star. It's a K-type star, which is quite small in the terms of the mass sort of scale of stars.
Okay.
So those are our 3 systems. Now, they were observed by TESS.
Yay.
Yeah.
Yay. Every podcast's favourite orbiting astronomical satellite.
Yeah, and the beauty of TESS is, of course, that TESS is a survey satellite, so it's moving around the sky, but when it points at a patch, it's pointing at a patch for about a month.
Okay.
Of sky, right? And it's pointing at a big patch of sky for about a month.
But it's designed to look for things which are changing.
Yeah, exactly.
That's the whole point.
It's trying to measure very, very, very tiny changes in brightnesses of stars. Let's be honest, largely so that we can find exoplanets.
It's in the name, right? Yeah.
Because what happens when you have an exoplanet move in between us and a star, you get a very, very tiny drop in brightness of 1% or less. And so it's got to have super great precision to be able to measure those brightness changes.
So it's looking at a pretty large patch of sky, but it's looking for very small, very specific changes on specific stars within that patch of sky.
Yeah.
Which is perfect for looking for micronovae, would seem.
Well, exactly,
Very
yes.
small, like not huge, massive, oh, look, there's a whole new star there, but rather that star just did something interesting.
Yeah. So although it's great for finding planets, it's great for looking at pulsations, as we've talked about as well. It's also great for just looking at, very small changes in the brightnesses of stars over time. And so that's what it was doing. It was looking, and it's returned and looked at each of these stars several times over its lifetime already. But it was able to find, for example, on the TV Columbae star, it had some bursts, little bursts of about 12 hours in duration of time. And these bursts rose very quickly. The burst rose in about half an hour, which
so you're looking at the
quite short.
When you say it rose, like that's the brightness. You're looking at the brightness of the star.
So it sort of was, if you imagine it was flat and then it rose up to some increased brightness, that whole process took about half an hour.
Okay.
So it's quick. And then it took about, maybe a day, maybe a bit less, maybe just a few hours to drop back down again. Yeah, because the whole thing was 12 hours. So it must have been 30 minutes up, 12 hours, the whole thing to get down. And that repeated 3 times in between, maybe about 3 days in between different bursts.
Right. And you said that Tess had looked at these on several occasions, had sort of gone back and revisited them. Was that because astronomers already had a sense that there was something interesting going on here? Or was it because the first time that Tess looked at it, they went, oh, there's something interesting going on there. We'll come back and have a look at that again? Or
it's neither, actually. It's just part of Tess's mission.
Right. They just...
Tess just...
Lots of data.
Yeah. If you imagine, like, there's a sphere that Tess is looking at. Basically, it just sort of clocks its way around the sphere, and it takes 13 times to do half a sphere. Then it flips itself over. It does the other hemisphere. It's got 13 different times, and then it comes back to the first one. And
Right.
Did it again.
So Tess is just looking, and it's up to the astronomers to figure out, what do we do with this?
Yeah.
And if you are looking in the right way, then you find it in the first time we looked at it, and the second time we looked at it, and the third time we looked at it, it's doing stuff.
Yeah. So these rises, and they were similar with the EI. There were 7-hour rises, separation of about 1 day, and kind of there were lots of little intricacies in that. But broadly, we were seeing these little kind of short rises happening over sort of much shorter time periods than a typical nova would.
And is it right? Do I remember you saying, again, this will be way back in one of our early podcasts, I think. But I seem to remember you saying, and it makes sense, that the size, like the physical size of something changing in a star or in a system will dictate how long it takes. In other words, the shorter a period of time that something like this is happening, that gives you a sense of, well, it must be quite small then.
Yes.
This must be a small thing that's happening physically in size.
Yeah.
Yeah.
Yeah, no, you're right. Yeah, that's called the light travel time. But I mean, generally we can even say, well, a full explosion of the whole outer atmosphere of a star takes on the orders of 10 days at least.
Right. Okay. So even though we talk about it as boom, like I imagine that happening incredibly quickly, you're still talking about a large thing that needs to happen.
Yeah.
And it takes time for that to happen over a large bit of space.
It takes some time to rise up, and then it takes even longer to sort of decay away.
Right.
So we know that these are much smaller because they're happening quicker, and they're actually expelling much less energy as well. So this is where your quotation, I'm going to blame your quotation here.
Okay, I'll take that.
Because it came out in all the press releases for this particular.
It's a new unit of measurement which I'd never come across before, and it just makes me laugh.
So I'll quote here. Each burn has 3.5 billion pyramids of Giza.
I mean, what?
Each explosion.
As in mass.
Yeah.
Like that's the equivalent of, turning that mass into energy. That's how much.
Yeah.
So what was it, 3.5?
3.5 billion pyramids of Giza.
I've got so many questions. Number one, clearly these astronomers have been listening to us, right? Because they heard my call and they said, well, we're not Egyptologists, but we can get this in there somewhere. And I would so love that to be true. Wouldn't that be fabulous if we then got a message saying, yeah, of course we put that in. It was because you asked for it. But my second thing is, why a pyramid of Giza? Like, they clearly think that gives us something from a sort of science communication point of view. They think that gives us something to hang on to. Oh, I've got in my mind's eye, I know what a pyramid looks like and roughly how big it is. But thirdly, that then completely goes out the window by the time you get up into huge numbers, because I've now lost any sense of how big this is. Like, how big is 3.5?
It's a terrible analogy.
Oh dear, but I mean, well done for trying.
Yeah,
I
mean, this is the kind of thing that you think, okay, yeah, you're trying really hard to make this imaginable, as you say, but I can't imagine 3.5 billion anything.
No,
I have no idea.
Let alone pyramids of Giza. I mean, I've got a rough idea of kinda how big that is. But if you were to ask me to estimate, I can't even remember from when we did the episode about the Pyramid of Giza as how big it is. I can't, and we actually did an episode about it. We talked at length, and I can't even remember that. So how am I supposed to? It's so good.
Yeah.
Just so good.
Yeah. Well, it's also bad.
Yeah,
perhaps.
but for someone who likes to collect interesting pieces of science communication, this certainly sits in the interesting basket.
Right. Well, we can break it down.
Okay. Can we
and
translate
I'm
this?
actually going to even offer you some alternatives
All
as
right.
part of this too.
Go on then. Let's do better.
One pyramid of Giza turns out to be something like 5.75 million tons.
All right. Let's call it 5 to 6 million tons.
Yeah. So if you have 3.5 billion of them,
yeah, that's a lot.
which we can't imagine, that turns out to be a number which is something like 2 times 10 to the 16 kilograms.
So it's just a stupid number of zeros.
Yeah.
Like, that's
not
a
useful,
lot.
right?
No.
So I can see them trying to break that down.
Yeah. What can we make this? Whales. Can we do blue whales is often one. Swimming pools full of stuff is a way to do volume. That's a very common one, but that's not going to help us here.
Neither of those are going to help us here. So
swimming pools full of whales. Can we? No, that's not going to.
Yeah. So let's find some things that might actually be of scale.
Okay. Yeah.
So I had to think about, well, you really got to go astronomical to get to the, sensible things to compare it.
Yeah.
to,
I mean, if it's not the Great Pyramids of Giza, then you're basically talking about chunks of the Earth. And at that point, we may as well just we've got chunks of things in space. Let's find one of those that's approximately the right size.
So it's about twice the mass of Phobos.
Phobos.
Which is one of the moons of Mars.
Okay. So twice the... Okay. So now we're able to talk about something which seems reasonable. I can imagine a moon. Now, the first thing I imagine when I imagine a moon is our moon. We're not nearly that big, are we? So how big is Phobos?
Well, Phobos is a bit of a potato-y kind of shape.
Yeah, I remember you saying.
But you can broadly approximate it as a cube being 20 kilometres on each side.
Wow, that is small, isn't it?
It is a little one.
Yeah. Okay. So I'm imagining a moon, but my imagining of the moon is probably far, far bigger than what we really want people to get across. So we could say Phobos for those who are Mars nuts and go, oh, a potato-y thing, 20. But
so that's option number one.
Or we could say 20 kilometre on a side cube of moon stuff. Yeah, cool. Okay, that's option one.
Yeah.
Can I just say, already we've blown several billion pyramids out of the water, right?
I think so.
I think we're already on a good wicket here. Yep.
Now, other one, this is a fractional one, but I thought it was quite nice. If you took all the mass and squeezed it together from all the rings of Saturn, so you took all the rings, squished them into one thing, then it's about 1/100th of that. I'm not sure that's particularly useful, though.
No, but I like it because it just sounds cool.
Yeah.
If you take the rings of Saturn, take 1/100th of that, we're starting to get a bit confusing.
So you can probably look at actually some of the individual rings. The mass of, say, some of the big brighter rings is probably about the same as that.
Yeah. I mean, you do sort of run into, would the average person on the street have any concept whatsoever about what we mean by that? And the answer is probably no. I'm still going with number one.
Right, okay.
Yep.
And the third one, which I thought would actually be quite nice and quite topical, if you remember last week, we actually spoke about a very, very large comet.
We did, yes.
Which was Comet
The
Bernardinelli
largest comet.
Bernstein. Yeah.
Asterisk, except for the other one.
Yeah. So it's about 40 times the mass of that comet.
Oh, okay, bunch of comets.
Yeah.
Yeah, 40 big comets
40
as
very big
opposed to
comets.
several billion big pyramids.
Yeah.
I'm going to go with 1 or 3. I still reckon a potato moon wins, but I reckon 40 big comets. Potato moon, 40 big comets. Yeah.
So I think, there we go. We can write to our friends who have written the press release for this.
You can have this one for free, right? Take your pick, one of these two. Or, 100th of Saturn's rings.
Here's a better way to maybe do mass comparison.
So, winding that one back then, remind us what we're talking about here. We're talking a small potato moon's worth of matter, worth of energy in every micronova.
Yeah.
Boom. Okay.
So how do we know that?
Yeah.
It's probably a good question.
We've gone a very long way to get to that point, but okay, here we are.
Well, I mean, it is actually reasonably straightforward. So we know how bright, or what the brightness changes has been for these little sort of these micronovae, and all you've got to do is look at how much the brightness has increased. If you've got your baseline, you know what where 0 is. You look at the brightness increase. You sort of sum up all the energy that it would take to get that brightness increase, and you actually directly get an energy out.
Yep.
So,
and energy is mass. Thanks, Albert Einstein.
Yeah.
And so you just go, oh, how many pyramids?
So my next argument would be, why do we even need to go to mass?
That's a very good question. Can't we just talk about energy?
Can we just talk about energy? Yeah.
So have we done that?
Well, I've got some energy here.
Give us some
I
energies.
like a little bit of energy. Now, I'm not super fond of the unit that the publication goes with.
Okay.
It's not my favourite unit. So we're looking at something like 10 to the 34 to 10 to the 35 ergs.
Okay. I mean, for starters, really big number. So what do you do with that? That's, again, like even more zeros than we had before. But an erg. What's an erg?
I don't even remember anymore. It's a small fraction of a joule.
That's just silly. No, let's not work with that. Let's do some translation.
So we'll go to joules because now a joule of energy is quite an easy one to imagine. I always think back to my kind of teenage science class definition of a joule, which is basically if you burn a peanut, I think you get a joule of energy.
I don't know that one, but I do now. I like it. How much is a joule? Go burn a peanut. There you go.
Something like that. Yeah. And then that's 10 to the 28 of joules. So it's not...
Still a lot. That's a lot of peanuts.
Yeah.
It's a lot of burning peanuts, I'm now imagining. That's probably, do you know what that is? That's probably a pyramid's worth of burning peanuts right there.
Well, let's find something that's a little bit more kind of relatable.
Sure.
So that 10 to the 28 joules of energy is roughly the equivalent of the kinetic energy of the moon going in its orbit around the Earth.
Wow. Okay. So kinetic energy being the type of energy that goes with things that move, right? It's your half mv squared from high school physics. And we know that the moon's big, and we know that it's going fairly quick. It's going around the Earth. So I can imagine that's a lot of energy. Yeah. I don't have a sense of really how much energy that is, but at least it gives me something to set my mind on. The kinetic energy of the moon.
That's option number one.
Sure.
Go with that one.
I'm okay with that.
Or option number two would be more or less the energy required to evaporate all the water on Earth.
Okay. Yep. So evaporation happens when you add energy to a liquid and you make the atoms, you shake the atoms a bit harder, and instead of all glomming together as a liquid, they start coming apart into their gaseous phase, and that takes energy.
Yeah.
So in order to vaporize all of the water on Earth, that's what we're talking.
Basically, yeah.
Okay, yeah. Because I don't know how much that is, but I know that the Earth's got a lot of water on it. And so boil all the oceans and all the rivers, that's it. Good, that's number two. I think I like both of these.
Yeah. Or the last one would be basically 1,000 times the amount of energy that the Earth receives from the sun in a year.
1,000 years worth of solar energy.
For the whole planet Earth.
Yeah. That's not bad. I can almost imagine that, you know? So I think all three of those are much, much better than a ludicrous number of pyramids that we've already converted from energy to mass.
Yeah.
Yeah.
But yeah, so then even if you did get that mass right in your head, then you've got to sort of figure out that actually a teeny tiny amount of mass converts to a lot of energy.
Yeah,
right?
Yeah. I mean, the Einstein thing is E equals mc squared, and c being the speed of light, which is 3 times 10 to the 8 meters per second. So square that, you're talking 10 to the 16, 10 to the 17. That's a really big number.
Yeah.
Times your mass is the amount of energy. So billions of pyramids times huge number. This is silly. We're just losing all sense here. I think I'm going to go with the 1,000 years worth of solar energy.
Yeah.
Kind of like that.
Yeah, it's nice, isn't it?
Yeah. Well, they can have any of those for free.
Yeah. So these micronovae release 1,000 times of what the sun hits onto the Earth every year.
Nice.
Yeah. So I guess the final question.
What are they? What's going on?
We found them. We figured out
now that we've
how
spent
energetic
a
they are.
quarter of the podcast arguing with researchers that we've never met. Sorry, everyone. About how to talk about these numbers. Let's get on to what are they? What's happening, Emily?
Well, we don't know.
That's the end of the podcast. Thank you.
We've only just seen them, but we have some clues. We have some clues. And like you said before, we know that these are smaller than novae, so they're probably not global white dwarf atmospheric events. So that means that they must be localized in some sort of way. So they must be localized to a specific region of the white dwarf system.
So this isn't sort of stuff being glommed onto the white dwarf all the way around it. This is happening in some particular spot.
Yeah.
So what could that be?
Well, that's a good question, because you can only blow up a small amount of the material that's around on the white dwarf in one particular location. So you got to detonate this stuff. You've got to kind of squish it together and get it hot enough, but only in one little place.
Only in one bit. Because it's still, like, just to be clear, it's still this sort of big thermonuclear explosion. Like, it's still the stuff falling onto the star and getting so hot that the nuclear reactions, the fusion reactions turn on the outside, which is still amazing. But it's only happening in one bit.
Yeah. And so probably the thing that's doing that are magnetic fields.
Right. I knew we were going to get there eventually, because we've got a really, really, really fast spinning, really compact, incredibly massive object, the white dwarf. It's going to have just nuts magnetic fields, right?
Exactly.
And magnetic fields tend to concentrate matter and stuff and energy and it can do that in like really quite small areas. I mean, one simple example is the poles of the Earth, where our magnetic field funnels stuff and causes the aurorae, the northern lights, the southern lights. But I mean, you see all sorts of wacky magnetic field stuff happening on the surface of the sun, right? With all sorts of flares and spots and weird stuff happening on really small scales. And that's just the sun.
Yeah.
So on a white dwarf, it must be mad.
Exactly, yeah. And I mean, kind of maybe even the same way that you have our next generation, or even current generation, of fusion reactors that we're trying to create. So the idea is you can take a plasma, which is just a kind of a soup of charged particles. You can use magnetic fields to confine it so that it doesn't melt the walls of your
best to
of your
avoid
container. And so using magnetic fields can be very, very powerful for very, very, very energetic plasmas. And that's, I guess, some
I know what they're doing.
idea, yeah.
Wow, that's really cool. White dwarfs making tiny little sort of fusion reactor tokamaks on their surfaces and blowing up.
But beyond that, I think there's going to be a future paper about what maybe the precise mechanism is for this localization with magnetic fields.
But that's really cool, right? Like, this is literally brand new. Like, this hasn't been seen and reported on before.
No.
We don't have a good idea, or we have some idea, but it hasn't sort of been textbookified yet as to what micronovae are.
Yeah, there might be some other analogies and other types of objects that we can draw from, but I think, again, that's going to be something left up to the future research.
I hope they do a bit of a better job than the whole pyramid thing. Well, Emily, I'm gonna say it now. We continue to push the boundaries of astronomical research through this podcast. I didn't actually believe that we were going to be able to influence how Egyptologists would continue their research, but the fact that we have managed to influence the way astronomers talk about amounts of energy happening in micronovae as a certain number of pyramids, while it isn't a good analogy, I think we're responsible for that. I don't know how I feel about that.
Well, I think we should definitely offer our consultancy services to anyone who is in need of a ancient Egyptian or other cultural
or not
astronomical analogy.
I think we could just do far better. I think people should just look, if you're putting together a grant proposal and you need some assistance in translating your numbers into something meaningful, give us a call. Emily, how could someone get in touch with us if that was a service they required?
Well, we can definitely get it down to just a few characters if you are on Twitter.
Yes, assuming Twitter still exists after being bought up by Elon Musk. But let's not go there in this podcast. How would they find us on Twitter?
So we are at SyzygyPod. That's SYZYGYPOD.
That sounds familiar. I know that we have that on some other platform that isn't owned by Elon Musk.
It is on the Instagrams.
Oh, that one that's owned by Mark Zuckerberg. This is not going well. But anyway, yeah. Instagram.
Well, do you want to try in the Facebook?
No, I don't, actually. It would be really nice to be able to say that there was some way that people could get in contact with us that wasn't owned by a billionaire.
What about just the internet on a web page?
That'll do. We're not billionaires yet. Syzygy.fm. Come and find us over there. You'll find all of the past episodes with all of the show notes, including the show notes that are linked to just our other episodes. And you can find a contact page on there where you can get in touch and ask for our consultancy services. Very reasonable prices. Do you know what else is a very reasonable price? Full of links today. Head on over to patreon.com/syzygypod, where you can become a financial supporter of the show, giving us money to help the electrons flow through our aforementioned website and help us to do all the things that we do on the podcast, whether that's just getting together to record this thing or doing live shows and events and festivals and all those kind of fun things that you get to do when the world is open up again. So, yeah, for just the price of a coffee, that tends to be the unit, not a pyramid, but a coffee, you can support the show every month and help us to do the things that we do. But the other way that you can support the show is to just tell everyone that you know that there's this cool thing called Syzygy, and they should listen because we're advancing astronomical research in every single episode. Emily, our next episode, not sure when that's going to be. It might be in a week.
We might be in a week. It might be in another time or place.
We might have to give you just a little bit of a break. We're just going to have to wait and see. It's going to be an exciting time, whatever happens. Fabulous to see you, as always. Catch you in a week or more, listener. See you soon.
See you later.
Bye, everybody.